Okay, now that we've understood how to count in situations when sampling is with replacement, let's move on to a setting where sampling is without replacement. So, let's change the problem a little bit. Right, balls and urns are getting a little old. Let's try this one. Again, the problem is quite elementary, right? But here's a metaphor. How many different ways are there of distributing 3 flags onto, say, 5 flagpoles? On retrospection, is there anything different from the previous problem? I replaced balls by flags, urns by sticks, but have I done anything fundamentally different? And a little thought might convince you that yes, oh yes, there might be one thing that's different. Perhaps it is not advisable to put 2 flags onto the same pole. One might start an international incident. Okay, so what could one do? Well, in which case, each flag has to have a distinguished pole all to itself. Oh, let's see what happens now. So, for example, the blue flag could go onto the 4th pole. The green flag could go onto the 1st pole. The purple flag could go onto the 2nd pole. Now, how would we describe this compactly? Well, in exactly the same way we did this before. All we have to do is agree on an order for flags, in this case, blue, green, purple, in that order, 1, 2, 3, and specify by number a triple of numbers identifying which flag sticks these flags landed on. So in our case, Bob's your uncle. There you go. 4, 1, 2. And that compact triple captures the mathematical essence of this entire problem. How do we abstract this? Of course, the numbers in these 3 locations could be quite arbitrary. And so here we go. If we put in 3 flags onto these 5 poles, the 3 locations could be specified by an ordered triple, J1, J2, J3. Again, J1 represents the location of the blue flag, J2 the location of the green flag, J3 the location of the purple flag. And now we want to count how many ways it's going to be possible to have such deployments. You understand, of course, that the metaphor of flags and poles here could be replaced by anything else you like. For example, we could have had 3 balls and 5 urns, and with the understanding that in this new experiment, an urn is not allowed to be reused. In other words, this is a question of sampling urns or flag sticks without replacement. Well, let's do the counting. The first number, the first flag, could go onto any of 5 poles. That gives you 5 possibilities. The moment you place a first flag on a pole, then you only have 4 poles left. Remember, sampling poles is without replacement. Which means that the second flag, the green flag, has got 4 possibilities to select from, and that leaves only 3 possibilities for the purple flag. By the basic rule of counting, independent possibilities multiply, and therefore the number of ways you can specify flag sticks for your 3 flags is 5 times 4 times 3. Now that's 60. But the number again is not particularly important for our purposes. The logic is what is important. Now this looks very much like what we had in the previous slide. There it was 5 times 5 times 5. Here it's 5 times 4 times 3 because resampling elements is prohibited. But the structure is very similar. It looks like a power. Well, why don't we put in some notation to capture this kind of structure, which is reminiscent of an ordinary power. We call this 5 times 4 times 3, 5 to the 3 falling. We represent it with a 5, with a power 3 and an underscore under 3 to remind ourselves that this is really not an ordinary common garden variety power that we saw in elementary school, but a new kind of power. This is a falling power. The 5 tells us we have a product of terms starting with 5. The 3 above tells us there are going to be 3 terms in the product, and the underscore tells us that each term is 1 less than the previous term. 5 times 4 times 3. This is sometimes called Pochhammer's symbol or the falling factorial, and we will see why in just a moment. Right. So again, symbolism, and this is supposed to evoke in you a familiar idea, the object of a power. But this is a slight variation on that particular theme. Now, once we've got this basic idea in place, we jump forward and we generalize everything. So, consider a population now, a set of n objects. So these n objects represent your n urns, your n flagsticks, or what have you. You're going to select from them, but the selection is going to be without replacement. So let's say we select k objects without replacement. We have an ordered sample of size k. How many are there? Well, the first number can be specified in n ways. Having specified one number, that particular flagstick is eschewed. You have to select from the remaining n minus 1 flagsticks for the next number, and then from the remaining n minus 2 for the number after that, and you go on through k terms. The last element is selected from n minus k minus 1 elements, which have already been specified. And so here we go. The number of ways in which we can select k objects in an ordered sample from a population of size n, where sampling is without replacement, is n to the k falling. A product of k terms starting at n, each term one less than the previous term. Now, before proceeding, I should say a word about this unusual terminology, falling factorial. Now, where does this come from? Let's go back one more time and take a look at this in a slightly sanitized setting. So, suppose we have 3 balls, our familiar peach, green, purple balls, and we are interested in how many different orderings of these balls we can achieve. So let's try to look at this. Right? So we can write down by inspection or by trial and error, by hit or miss, a certain sequence of balls. And they appear on your screen on your left. How do we know we've got all arrangements? Right? There are 6 different arrangements. And the idea is to be very, 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 very systematic. Right? So this is an example of what's called a lexicographic arrangement. Right? Now, in combinatorial settings, it is exigent that we are very precise. We don't miss elements and we don't double count elements. These, in fact, are the 2 golden rules of combinatorics. Don't overcount and don't undercount. Of course, it sounds completely banal and trite, right? Of course, you don't want to overcount and you don't want to undercount. How do you avoid overcounting? How do you avoid undercounting? The idea is to be very systematic, to set things up as you would, for example, in the index of a book, or when you count pages. This is the lexicon, and that is the basis of a lexicographic arrangement. A is before B, is before C, 1 is before 2, is before 3, and in our dictionary of translation, green is before purple, is before peach. And then you go ahead and set up very systematically a system of arrangements. And we have 6. This is excellent. Now, let's put this in the context of sampling. Suppose we start with a population, a set of n distinct objects. How many different ways can these objects be arranged? In the balls in front of you, you've got an arrangement of 3 objects, and there are 6 possible arrangements. Now, when you think about n objects, you realize that what we are trying to do is specify a sequence, an ordered sequence of n objects where no object is repeated. That is what we mean by an arrangement, a permutation. In other words, every such arrangement results in an ordered sample of n elements. In this case, k is equal to n. These are selected from a population without replacement from a population of n elements, which means that every one of your n elements in the population appears exactly once in this ordered sample. Oh, but we know the answer to this. When we selected k without replacement from a population of size n, we had n to the k falling possibilities. when we select n out of a population of size n, then by definition we have n to the n falling. Recall that this falling notation means that you start a product at n. The thing in the exponent tells you how many terms there are in the product. In this case, there are n terms in the product. And each term is one less than the previous term. And when you work it through, you find you start at n, n minus 1, n minus 2, and by the time you get to the nth or last term, you hit 1. In other words, on the right, you have a product of all the numbers from 1 through n. Of course, we have another name for this. This is what we call the factorial, n factorial. So this is now the origin of the terminology, a falling factorial notation. If you look at n to the k falling, and you select k to be n itself, you get back n factorial. And so now this is a mnemonic, a visual feature which tells you what this thing means. It is related to a factorial. You know, it's very much like a duck you might observe, right? If you see an object, if it walks like a duck, if it quacks like a duck, well, it's got to be a duck. If this thing walks like a factorial, if it quacks like a factorial, well, it's got to be a factorial. And therefore we call it a factorial, or more precisely, a falling factorial. Now, a little convention makes our life easier, smooths our analysis path. What if n is 0? By convention, we say that 0 factorial is 1. Thus far, we've looked at settings where we have an ordered sample from an underlying finite set or population, and the sampling was with or without replacement, and the counts, therefore, became ordinary powers or falling powers. Now let's move on to a setting where we extract a subpopulation, in other words, a sample without an implicit order from the population at large.